algebra trick that you're going to either already know, and this will just be a refresher on, or this might be the first time you've seen this. Um, this is really an optional trick, one that I think you'll develop as time goes on, even if you're uncomfortable with it now. So let's jump right in. So, um, one of the big things uh, when we're talking about using physics and algebra together to solve problems is that we want to especially highlight your understanding instead of memorization. Physics is really about understanding how the world works. It's not about memorizing facts. So understanding, in our opinion, is much more useful than memorization. Now, in a bunch of ways, you sort of de facto memorize things. By that I mean I know how many meters are in a kilometer, but not because I memorized that fact. It's because I have used that fact enough that it just sort of muscle memory sticks around in my brain. You're going to learn many algebra tricks and many math things that are going to be useful in your math classes, but we're always going to teach you why the trick works, not just, hey, here's this trick, memorize it. Um, the bottom line is get the math right, know what you're doing, and then you don't have to worry about it too much. And trust me, you will internalize or learn these tricks just like you would learn a sport or learn a hobby or a skill. Um, where my perspective, this is Mr. Hipperman talking, where my perspective comes from on this, it's reinforced by one of my favorite physicists, Richard Feynman. If you hang out around physics circles for very long, you're going to hear this name. This quote from him I love. He says, quote, "They didn't put two and two together. They didn't even know what they knew. I don't know what's the matter with people. They don't learn by understanding. They learn by some other way, by rote or something. Their knowledge is so fragile." So to clarify, by rote, that's sort of an old term, but that means rote memorization or just purely memorizing. He's saying that learning by understanding is so much more powerful and deep than learning by memorizing. So there you have it from one of my favorites. Anyway, I'm going to show you this algebra trick. So we're going to try to see if we can notice a pattern by solving similar algebra problems in the same way. So in this example, we've got this equation. Acceleration is velocity over time. We're going to try to solve this equation for time. So you guys know how to do this. What we would need to do to get time off the bottom is to multiply both sides by t, so that t's on the right side cancel, and we're left with just t times a equals v. Now we need to get the a off of the left-hand side, so of course we need to divide both sides by a. That looks like this. Those a's on the left will cancel, and we're left with t all alone. T equals v over a. Nice. All right, let's do that again with a more complicated one. Here we've got a square root. We want to get g by itself. Here g would be like the acceleration due to gravity. You might remember that from physics 1. So anyway, what we need to do first, there's a bunch of ways we could do it, but I think the easiest way is to just square everything first. So everybody's getting squared to get rid of that square root. So the TP gets squared, the 2 gets squared, the pi gets squared, and then that square root goes away. Simplify that just a little bit. I'm going to put the 2 squared, which is 4, and the pi squared up top with L. Put the g on the bottom. Looks good. Now we need to get g over on the left and tp on the right. So let's multiply by g. We've got g on the bottom. Let's multiply. It's going to cancel on the right and now end up on the left. So we have g tp squared and all the same stuff on the right-hand side. We'd love to get the tp squared out of there. So divide by that on all sides. Cancels on the left, and we're left with g solved by itself. We actually will do a lab this year where you'll measure g with a pendulum. Remember, it's around 9.8. Cool. Let's do that same thing. This comes out of your packet as well. We're trying to solve for L, and then we'll solve for D. You could solve for any one of those variables if you like. So we've got on the left x over L equals, on the right-hand side, we have a Greek letter called lambda over D. So I want to get, let's solve for D first. I think that's what we're going to solve for first. So I need to multiply by L on both sides to get it out of the bottom, and we're going to move it to the right. So on the left, the L's will cancel, and the L times lambda will go on top of the fraction on the right. We have x alone there. So if we wanted to stop and say, hey, we've got x alone, we'd be good. But we actually, we want to get D by its, no, we're trying to get L by itself. Sorry, I've just seen that now. So I'm going to do 2 steps here at once. I'm going to divide by lambda by multiplying by 1 over lambda. And I'm going to multiply by d. I'm going to do those steps. I'm going to kind of mush them together. It's sort of like multiplying by a reciprocal fraction. So on both sides, we're going to multiply by d over lambda. See if you can think for just a moment what's going to happen. Pause the video if you need to. Okay, so the d's will go away. My lambdas will go away, all on the right-hand side, and we just end up with dx over lambda on the left. Check me there, make sure I'm right on that. So we've solved for L. I want to walk you through a similar process. We're now going to solve for D. So we need to get D off the bottom, multiply by D on both sides. So we have on the left dx over L. On the right, we have lambda. Now, if we were trying to just solve for lambda, we would be done. Instead, we need to go a step further. We need to get D by itself. So I'm going to do that same trick. I'm going to multiply by the reciprocal on the left-hand side. So we have x on top, which means when I'm multiplying, it should go on the bottom. L's on the bottom. When we multiply, it should go on the top. So not surprisingly, we're going to multiply both sides by L over x. Take just a moment. Pause if you need to. Double check what's going to happen. Everybody cancels where we want it to cancel, and we end up with D equals lambda times L all over x. And there we have it solved for D. So you might be wondering, where the heck is he going with this? Well, I just did 4 examples. I'm going to put them back on the screen for you. We want to see if we notice a pattern, and I'm going to spoil the pattern for you. All the diagonal variables just switch. So let's go slowly through the first 2, and then you'll see what I mean. So right here, we have a equals v over t. Notice in the final answer that t and a just switch. It's kind of weird. Well, it's not always the case in math that you can just notice a pattern and it will carry on forever. I want to show you why this actually works all the time. In this next one, you've got tp squared, time for a pendulum squared, and then on the other side, you've got g on the bottom of the fraction, and they end up, if you go back and look at our math, they end up just switching again. If we do the same thing, I'm going to rush through these last 2, but you end up just switching where the variables are. So the L moved up, the lambda moved down, the D moved up. In this case, the D moved up and the X moved down, and the L went up with the lambda. Now, why does that work? Well, let's take one of our simple examples. We start with A equals V over T, and we end up just switching the A and the T. Why does that work? Well, if we go back to the actual steps, and this is, if you go back to all of the steps, this is what we did. We multiplied, okay, by t to get it out of there, and then later on, we divided. So remember, I'm not asking you to memorize this. We just did the same thing over and over. So if you were writing this out, you'd start to see a pattern develop. Okay, you can try this on your own. So there's 2 algebra steps, and all I'm saying here is that we should smush them together into one. So we are just combining the multiply and divide steps into one step, and I promise that's allowed. You could even do it divide then multiply. It doesn't really matter. But we want to make sure you understand why this works, not just do it. Okay? So, for example, a lot of times students will remember that there's a trick, but they don't really remember why it works. And I would say to those students, don't use the trick. Okay? Keep working on your muscle memory. Keep solving them sort of the quote long way. Okay, it's the safer way in my opinion. So for example, maybe they're given a question, that same one, solve for t. They're like, I remember there's some switching. Maybe I can switch a and v and solve for t that way. So yeah, like quoting an imaginary student here. I remember that I can just switch the variables. I hope this is right. And so they'll somehow end up with v times a equals t. Now when we're talking about physics, this solution is very different from the correct solution. That is wrong. You'll notice they did something like, yeah, sorry, had my fun little animation. That's wrong, right? That is not correct. Somehow they turned 1 over t into just plain old t. And those are the kinds of things that we don't want to see. This student clearly poorly memorized the trick by not developing their muscle memory, and they got the question wrong. The bottom line is we just want you to get the questions correct. So last thing here, be careful. If you're not 100% sure about the trick, just don't use it. It's only one extra algebra step. It's going to be fine. All we did was combine 2 algebra steps into one. And as I said, you're most likely to just develop this over the course of maybe the first 9 weeks or over the first half of the year. Maybe by the end of the year, you start to use this trick. So just be careful and good luck. Thanks, guys.